So now we don't allow short selling, which means y is bigger than or equal to 0. If we don't allow short selling, then y is not going to be negative, so hy can be written as y divided by 2. We don't need the absolute value anymore. And so we are in a familiar territory now. We assume r equal to 0. Now we assume initial value of the cash to be $10 and 1 bushel of wheat to begin with. V1, V2 is still equal to 1. And we assume t equal to 3. And we assume the price forecast to be like this. Not 3 and 4, but something that decreases for a while and increases. So it decreases up to 2, and then from 2 to 3, from time 2 to 3, it goes up. The terminal wealth is x3 plus 4 times y3, because remember that price at t equal to 3 is 4. So we can evaluate our wealth by the value of the wheat plus our cash. X dot is my half minus half y times PV, y dot V. So this is standard, but we write the boundary conditions here. We now going to use chapter 4 formulation. Chapter 4 formulation, we write the constraints to be inequalities. So v bigger than or equal to -1 and v smaller than 1, it basically reflects these two bounds. And y bigger than 0 is our state constraint. Okay? Chapter 4, we apply maximum principle. Then Hamiltonian is lambda 1 times minus y2 minus PV plus lambda 2 times V. The optimal control is bang bang. When y is bigger than 0, it's bang bang from -1 to +1. But when y equal to 0, indirect maximum principle, we should impose a constraint y dot v equal to 0 in the Lagrangian. And in order to ensure that no short selling occurs, then our bang bang control has to go from 0 to 1, because we cannot sell when y is 0. We can only buy. And so we can only buy from 0 to 1 and buy according to this quantity when y equal to 0. The indirect Lagrangian is h. Then you adjoin the two constraints, which are these constraints, these ones. And then we have a eta times v, which is the constraint on y dot, which is v bigger than 0. We put this constraint. Then the maximum principle says complementary slackness conditions are given by, this is on mu1, this is mu2, this is on eta. Remember, we don't put eta dot less than 0. That was a remark. And we don't use that remark, although you could. But this is the maximum principle right now that we use. Delta L delta V is the maximizing the Lagrangian or first order condition of Lagrangian rather than maximize Hamiltonian, which comes subject to constraint, which is the first order condition of Lagrangian, is equal to 0. And with r equal to 0 and lambda 1 equal to 1, lambda 2 dot is half. And lambda 2, 3 minus, which is you apply the chapter 4 maximum principle, is lambda 2, 3 minus is this, equal to 4 plus gamma. You notice there's a gamma that's coming in there because the constraint, and gamma bigger than 0, gamma y3 equal to 0. So this is the condition of maximum principle that we have. And then we have condition on jump. When there's a jump in y, there is when there's a constraint encountered, there is a jump condition that will come also as part of this formulation. But that we will get that when we get to that jump. Okay. So we don't know gamma. We're going to start backward. So we're going to assume either gamma equal to 0 or a gamma bigger than 0, and I'm assuming here gamma equal to 0 and see if that works. If gamma equal to 0, then lambda 2, 3 minus is exactly equal to 4. And that means there is actually no jump at 4. And if we so now let t hat be the last jump before the terminal time. That means that there's no interval in this, there's no jump in this interval, t hat to 3. So in this open interval, I can solve for lambda 2 because lambda 2 is basically lambda 2 is just the slope of half right there. So I can solve the condition by giving this condition, boundary condition, and the half slope. I have this solution, which is easy to see. You can see at 3, this becomes 3 by 2 plus 5 by 2, which is exactly 4. Okay. 3 plus 5, 8 divided by 2, which is 4. So this is from t hat to 3. But we don't know t hat yet. So we have two arguments here. One is that the optimal control from 6.67 and 6.68 is v star equal to 1. That is by v at the maximum rate of 1. Let's see what's going on here. Let's look at the picture. You can see that this is my lambda from, this is t hat. We'll see what the t hat is right now. This is my lambda, which is about this price trajectory. So in this interval, at least close to 4, I'm going to buy. And if I'm going to buy, first of all, if I'm going to buy, then gamma 0 is a good thing because I will have no constraint here. Y will be positive. Y will be strictly positive here, and so gamma will be 0. So so assuming, yeah. So with that assumption, we are constructing a solution. So when we construct that solution, we see that we're going to buy here. Well, notice that buy can start as long as this guy is bigger than P. And if we keep going that way from this point 4, we will see that there is a point which is 1.8 that we can actually buy all of this. So clearly, there is no jump between 1.8 and 3. So t hat is 1.8. So this is what we're going to next. We don't know if it's the jump point, but let's go back there, and we have to just go back forth. So that what I just said says that t hat cannot be above 1.8. Remember, this is the last jump. So last jump t hat has to be earlier than 1.8 or at 1.8. Okay, so that's what we can conclude from this. Let's go to the next point, saying that in the beginning, PT is decreasing. So it appears that selling at the maximum rate should be optimal at the start. Again, we are guessing for a while, but the guesses are reasonable because I have a wheat in the beginning, and the price is going down. And notice it is easier to see what's going on here. Price is right now here, and the price is going down. I have a 1 bushel of wheat. I certainly cannot keep that bushel of wheat more than 2 periods of time, because 2 periods of time I will eat up the $1 holding cost. And if I keep it all the way up to here, I'm going to lose on the price as well as holding cost. So I'm going to start selling. Okay. When I start selling, I can only sell 1 unit. That's all I got. So my selling will finish at 0.1. If I start selling at 0, at the rate 1, I will have a 0 unit of wheat at this point. At this point, I cannot buy because price is going down. So buying is no good. And if I buy all the way for a price going up here, maybe there'll be very high price here. That's no good because that's too far from 1. It's 2 units later. So 2 units later, it's okay. But I can keep the wheat for 2 units later if it is very large amount here. But that conclusion is not completely important yet because we need to see the price in between two. But we can easily conclude that we cannot, what we have right now, we cannot do anything. We cannot sell because we are out of wheat. We cannot do short selling, and we cannot buy because we are in a situation where buying is no good because price is going down. That means that at this particular point 1, I will do nothing. If I do nothing, I would have to have a singular control. Singular control means V star equal to 0. Singular control in our setting means P2 equal to lambda 2. So in the beginning, I can sort of see that lambda 2 would equate PT at 1. So that's my condition on lambda 2 at 1. Then I can solve the equation for lambda from 1 all the way to 0 backward. The slope is half, so I can see that it goes to 5, and so at 0 it will be 4.5. It goes from 4.5 to 5 in one time unit. So that's my lambda. Okay? And I do nothing here. If I do nothing here, then I can continue all the way here because the entry point is here. I entered the constraint. The constraint was y equal to 0. So when I sold the wheat, I entered the constraint here. I did not enter the constraint at 1.8. So at 1.8, lambda is continuous. Lambda 2 is continuous. So I can continue lambda 2 all the way up to 1. Okay? So now you can see what's going on. I'm selling here. I'm buying here. And I'm doing nothing here. So that has to be, when I'm doing nothing here, then I need to find the jump at the entry point. Because the singular control began here. And this is the entry point. So the jump, there may be a jump, there may not be a jump. I need to find whatever it is. So that's what I use the Hamiltonian condition. So you see, I have a lambda, I have this. Now what is going on here? If I proceed further, then my lambda is lower than P. When my lambda is lower than P, then Minmin says his mic doesn't work. Well, Kusali, you take care of that. Figure out what to do. Okay, so what I'm trying to say is, okay. So what I'm trying to say is that we are in a bang situation, but a bang situation is of this kind. You see what I hear? It's this kind. When it is bigger than 0, I buy. When it is less than 0, I sell. But I sell, but I have nothing to sell, so I make it 0. So this is this particular condition, I 0. So as you can see here, if you look at it, I'm exactly in the situation of that bang because I'm below the price. The lambda, this lambda right now up to here is above the price, but after this lambda, below this lambda has already gone below the price. So if it's below the price, I would like to sell, but I have nothing to sell. So the second bang condition applies and V star is 0. Do nothing. When V star is 0, Y equal to 0. Because I already entered the wheat and Y equal to 0 constraint continues up to the point when I start buying again. So from 1 to 1.8, I'm on the boundary of the constraint. So once I see this, in fact, if you see what's going on, I already, if I go all the way this, and 1.8 is continuous, I can continue all of that. I already have the jump geometrically. Now, jump is geometrically, but I must still find out if the Hamiltonian condition holds. Because the Hamiltonian condition doesn't hold, then maybe my gamma that I said was not correct. And maybe some other things have to happen. So let's now, so you see all of the things. So everything is done here. And I already know what V star is on this side and what V star is on this side. I already know what lambda 2 is on this side and lambda 2 on this side. Okay, P is continuous, so it's on same on both sides. Only thing that is discontinuous is a P and a lambda. Okay, so P and a lambda both go into the Hamiltonian. So let's go to the Hamiltonian condition. So you see, all of that is done. So if you go back here, so first I found 1.8. Then I went in the beginning. In the beginning, I said I'm going to start selling. So I start selling. And I said 1 point lambda 2 is continuous. So I can go lambda 2 all the way from 1 to 3. So that allows me to have a lambda. And then I substitute those conditions here in my Lagrangian condition. So I can conclude that in 1 to 1.8, V star is 0. So that mu1 and mu2 equal to 0. Because these are the complementary slackness conditions associated with this. So we have, then when that is 0, then I can have, I can write this equation as this equation. And that gives me eta t equal to P2 minus lambda t. So I can get all of these guys. And I'm ready for my Hamiltonian condition. So the picture is very good. It cuts through all the writing that we have. So now we need the Hamiltonian to be continuous because small ht is 0. So the jump says the Hamiltonian should be continuous at t hat equal to 1. T hat is our entry point. So which is tau as in our formulation. So tau equal to t hat equal to 1. X star 1, this is the control, P, this is lambda 2, this is time 1, this is time 1, this is plus, so I can put all of those values. So applying that condition, which comes from 4.29, we have lambda 1 minus y1 da 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 equal to this. So the above condition, because lambda 1 is 1 and is continuous everywhere, so the lambda 1 can be substituted and I have a condition like this. Now I substitute. Okay, P1 minus and P1 plus are the same. V star 1 minus is minus 1 because we are on 1 minus we are selling. V star 1 plus is 0 because we are doing nothing. Lambda 2 minus 1 is the point at the price trajectory, which is right here. And that guy is right here. So we can substitute the value lambda 2, 1, and plus 1. And I see here. Substituting the value this, we get P1 minus, or this is equal to 5. And so anyway, I'm substituting these values. When I substitute these values, I get lambda 1 minus equal to 5. I actually get lambda 1 minus equal to 5 by substituting this. And using the jump condition, I have zeta 1, which is the jump, which is equal to 2. So you can see that I actually got lambda 1 minus equal to 5 exactly here. So my Hamiltonian condition starting at this point, I already know the condition of this point. I can conclude the condition on this point. I did this here geometrically, but the argument is that I jump here, I come here, and then I go there because I'm solving backward. So I can do up to here, But in order to go from there to there, I need to find out what the value of the jump is. Once I know the jump, I can continue. And the jump lands me exactly on this point, which is what we thought is going to happen when we started from this quantity. Okay. So this whole idea of constructing a solution like this is important, and it will become more complicated, but this idea will help us through to cut through the chase and get the solution to the next period. Now, this is where some innovations are taking place at that time. It turns out that you can sort of see that this optimal solution may remain optimal even if I change the price forecast a little bit. So let's see what's going on here. So I'm gonna now get the ideas of decision and forecast horizon. So let's just go here for a while and let's go to here. Suppose I change the price like this. So instead of my price, which goes like this and goes like this, I change it like this. It turns out that if you change it like this, I can go backward again like this up to here, find the jump, go up to here. What is my new solution? My new solution is sell, do nothing up to this point, whatever that point is, then buy and then sell. Notice I changed the solution in this interval, but this stays the same. And I changed the forecast, and this stays the same. What I'm now trying to say is that as long as this price trajectory stays below this price shield, I call it a price shield. This is first time in this book, when we wrote the book. This is again a material that is original. We have a price shield, and as long as the price is under the price shield, I will have a solution changing here, but that solution will not change. So what I'm now saying is that this decision doesn't change regardless of what the forecast is, as long as the forecast is below the price shield. Because it requires some constraint on it's some bound on the forecast, I call it a weak forecast horizon. Suppose I didn't put this constraint. Suppose I can do whatever I want here, and this solution doesn't change. Then I will call 3 to be a forecast horizon. Okay. Notice also that you can see that the forecast horizon is already here. That means I can change any forecast from here to there. So what I'm now trying to say is the following. Suppose I solve the one period problem, just one period problem, and I have this forecast up to here. My solution is sell. Now suppose I change 1 to 2 to 3 to 5, whatever, and I have a forecast from this point on that is staying below the price sheet. The price sheet continues. Stay below the price sheet. This is not going to change. So what we have is this is horizon of 1 and a weak forecast horizon of 1. Weak because I have the price sheet. Next model that I'm going to do, I'm going to try to remove this price sheet. I'm now going to create another problem in which I can have any forecast I want. And I want a place called forecast horizon and a place called decision horizon. So what is the forecast horizon? What is a strong forecast horizon? What is a decision horizon? A strong forecast horizon is a time period, okay, and a forecast given up to that time period, and a solution that is created for this time period for that forecast. Suppose I can find one point here such that the decision of this part doesn't change no matter what I do to the forecast beyond this forecast horizon. Whatever forecast. I don't want to change the forecast between the decision horizon and the forecast horizon. But I can change the forecast beyond the forecast horizon as much as I want. Okay? So now we're going to try to find a strong forecast horizon. Okay, so this problem is done. There is some definition of strong forecast horizon, final horizon already. He says if the condition during the decision horizon are completely independent of the data beyond the forecast horizon, then the latter is called the strong forecast horizon. Okay, weak if there's a mild restrictions. Okay, these are terminology that I introduced in the literature, and the terminology is followed by other people in other contexts where such forecast horizons exist. So I'm now going to do the following. In the previous problem, I'm going to introduce a warehousing constraint. Okay, I introduce a warehousing constraint, and that means my warehouse can only hold 1 unit of wheat, and I cannot buy more than one. I cannot have more than 1 unit of wheat in my warehouse. Under that condition, what would be the solution? And what I want to do now is give you a problem. So here's, you can all do all of that. And now because of the constraint y less than 1, I also need a complementary slackness condition on this parameter eta1, which is a new parameter. Remember, y dot less than 1, that when you do this, the derivative is minus v, and eta1 times minus v is the term in the Lagrangian. And I can do all of that. And then I have a gamma 1, gamma 2, and all of these complementary slack condition on gamma 1 and gamma 2. And I'm going to start assuming gamma 1, gamma 2 equal to 0. Let's see, we can come back here, but let's see what we're trying to do. Here's what I'm trying to do. What I'm trying to do is the following. This is my forecast. I have a 4 periods now instead of 3. And I'm going to start from there. If I start from there with gamma 1, gamma 2 equal to 0, then I will do nothing. And if I go from here, I will sell. And then what happens is that I need to find out that I need to buy because the price is going up. I need to buy, but I cannot buy more than 1 unit. So I need a line of slope of half, because in lambda dot is half, because y is positive, so there's no absolute value of y. It's always half. There's no signum function here. If I take the value of half, this is the slope of half. I cannot do anything here. That means whatever I buy, it must stop at this point. Okay. That means that if I take this half slope and I roll the pencil, put a pencil along this and roll the pencil so that I have a parallel lines going up and down. Now, I need to stop at a point where that point and that point is 1 point apart, because this is the time when my lambda is above the price forecast. When lambda is above the price forecast, I buy. But I can only buy 1 unit of time, no more, no less. I mean, I can buy less, but I can buy more. But I cannot buy more. But given that I can buy, given the price here, that point has to be 1 unit. So once that is 1 unit, I can extend that all the way to here. We'll go through the arguments one by one. But now that's kind of what is going on here. And there will be a jump here, because I'm encountering the state constraint of 0. And there will be a jump here because when I'm buying, I have to stop buying at when my wheat balance goes to 1, I have another constraint, which is the y less than equal to 1 constraint. So when I encounter that constraint, there may be another jump. So here's the entry to 0, y equal to 0 constraint. Here's the entry to y equal to 1 constraint. Here's one jump, here's another jump. You can now see that our program gives us a solution where the lambda starts from here, then jumps downward, all the go here, then jumps up and go up to here. And the price forecast is like this, price is like this. So here I do nothing because because I want to sell. No, because I want to buy, but I cannot buy anymore because my warehouse is full. Here I want to sell more, but I cannot sell anymore because I already have no wheat left. So I have to do nothing, and I have to do nothing here. So that's kind of optimal solution. The next part of the optimal solution is what is a forecast horizon, what is a flying horizon. We will show by examples. I can also prove it, but let's just do examples. That this point 17.6 is a strong forecast horizon. That this point 1 is a decision horizon. That means if you give me a problem of this horizon and give me the forecast up to this point, that forecast will give me that solution. And that solution up to here, that solution has this decision in 0 to 1. I will now show later that if I change my time horizon to anywhere after 17.6, anywhere, all the way, and I can change the forecast anything I want from here on. I don't care about the price shield anymore. I can do whatever I want. This decision will still remain. So that is a strong forecast horizon. It doesn't depend on the forecast. Beyond the forecast horizon, it doesn't depend on how many periods I want to go. So this is in some sense saying, I don't know how long my company is going to last. I don't know what the forecast is going to be for a long time. But regardless of what happens, I can make this decision willy-nilly. Only constraint is that that forecast from 1 to 17.6 cannot change. And that is a huge constraint because if I'm at 1 and if I find the forecast is changed, I cannot say this is optimal anymore because forecast is changed. And I cannot say that forecast should not change because it's changed, it's changed. There's nothing I can do about it. And to deal with that problem, I wrote a paper called Rolling Horizon Decision Making. And that paper gets cited and gets downloaded on SSR and is one of my top papers. But I can only tell you that no one has done anything beyond that paper because the technology that I developed there is so computationally intensive that all one can do is do some approximation, and I have not done anything myself, and no one has done. And so that paper just stays exactly as the theory of rolling horizon decision making all by itself. But that's not our concern here. I'm just telling you that the limitation of the forecast horizon allowed me to go further, but that further is nothing to do with control theory. It's a fancy dynamic programming and stopping time problems, but we don't want to get into that. So let's now go back and see what we have done so far, and then we will also see how this remains the optimal solution when I change things here. So t equal to 4, this is a new constraint, same forecast. I have now 3 bang bang. One is when I'm interior, one when I'm at 0, so I cannot sell anymore. One am I 1, so I cannot buy anymore. So this becomes -1 to 0. This is from 0 to 1. This becomes -1 to 1. So this is easy to do. This is chapter 4. Now we can do the Hamiltonian business. This is easy to do. You have a Hamiltonian multiplying by the two indirect constraints, indirectly the constraints. Then I have a this I'm going to remove this. Is that removed in the book? We'll see. Okay. Um, so chapter 4, following maximum principle, I should not have this. So I get delta V equal to 0. You will realize that all of these will be satisfied, but we still don't know whether in general it satisfies and whether this will give us an extra reduction in a candidate space, which is good for me. But anyway, let's not get there. So by doing this, I'm now going to go fast. I'm going to get the last jump. The last jump has to be t hat. Then I can solve the problem from there to t hat. So that is the graph that intersects at 8, 5. It also stays above the previous trajectory in the interval this. And if there were no warehousing constraint, the optimal decision in this interval would be to buy at the maximum rate. But if there is a warehousing constraint, then it's going to be do nothing. However, with the constraint 6.2, this is not possible. Thus, t hat is bigger than 8.5, and since lambda 2 will have a jump in the interval 8.5 to 4. That's what we are now doing here. So once we do that, we can find the actual value at the minimum price at t equal to 2 in such a way that it's 2 intersection point. The price are exactly at 1 time unit apart. That's what I said here. We need that line of half slope so that intersection with the price trajectory of that line is exactly 1 unit apart. And that's why I did that. And that allows us to find the t hat. And then the gamma 1 equal to gamma 2 is a correct guess. And I can write the whole trajectory in interval 0, 1, so the entire thing is written. Now what we are going to do, we are going to do variations on this, and to show that no matter what I do, this solution is still remains. So let's now have a price trajectory of this kind. And I will give you the figure. So now my new price trajectory is starting from here, go there, and then go there. This is my new price trajectory. And my solution now will be do nothing up to here. Different solutions. So this is still 17.6. And then a jump up from this side or jump down from that side. Then I go here. I still buy 1 here. I do nothing here, and I still sell. So this is still a forecast decision horizon, and this is still a strong forecast horizon. Remember, I changed the forecast. It's way beyond price shield. So it works. Okay, so this one. Let's do one more thing. Now assume the price trajectory. Now assume the price trajectory why am I done here? Oh, there's another picture here. So I'm sorry, I get too far. So now assume the price trajectory. So here's what happens. If I have a price trajectory, which is given by this formula, then I actually have a price trajectory which goes like this, goes like this, goes like this. And if you were to solve this problem going this way, you will find that at some point or another, you will see that what I need is something somewhat different because things are changing here. So the way it has happened now is that I sell here, then I do nothing. But then I have a slope of line during which I can make some profit. That means during this time, there is enough opportunity for me to make a profit. But I don't want to keep the wheat beyond certain point because price is going down. So my wealth will not be very good if I keep this wheat and also pay the holding cost. So I have an opportunity here where I can buy and sell, but I must buy at some point and sell at some point so that whatever I buy, because I remember I have nothing here left. So my warehouse is empty. So whatever I buy, I must be able to sell because I don't want to keep it. So here's a line of slope half, and it must intersect in such a way that amount of buying and amount of selling is equal. That means this time and that time are equal. So I will buy whatever I'll buy, I will sell that same amount. And there will be a point at which that line will cross, but that's not important. What's important is that this point and this point are one unit apart. And once we have that, we can write all the conditions of the maximum principle. And this particular one basically can be obtained this way because you have this point and that point, and you have slope of half, and you can find out the T1 hat. Once you do that, you actually have the whole solution. You can build the whole solution. You can write. I think this may be one of the exercises. You can write all of these guys. But the important thing to point out is that the decision horizon stays. So to some extent, if I have some good idea of forecast that gives me a price shield, I can make an initial decision in an optimal fashion. Or if I have, if I limit myself to not changing the forecast here, which is not in my control, unfortunately, but under that assumption, I can guarantee that this is optimal. Although that assumption may not be a good assumption because whatever happens to forecast, it happens. But in a rolling horizon, what you do is you make a decision up to decision horizon, then you make a forecast again, and you resolve the problem. Again, find a new forecast horizon, resolve the problem, and go to the next decision horizon, and again do the same thing and go to the next horizon, and keep doing it. That's the rolling horizon decision making procedure. That can be implemented using this formulation. But in what sense is it optimal? That one is in the paper of rolling horizon decision making. How and what kind of criteria and a formulation allows us to say that what we are doing in the rolling horizon fashion, in fact, is an optimal solution starting at time zero. That means we can say that we behave optimally for all these forecasts. Okay, that is in that paper. Okay, so we are 10 minutes from the class. Are there any questions?
Hi, Professor. Can you hear me?
Let me, you have to speak loudly. I cannot hear. So let me see if I can change my volume here. Where is my volume here? Oh, speaker. Oh, my volume is very high. Now I am at 100. Okay, continue.
Can you hear me right now?
Yes.
Okay. My question is about gamma. I mean, I noticed that for many questions and also the examples before, we started with a guess about lambda equals to 0, and we solve those problems and everything's fine. And my question is, what is the situation that gamma is not 0?
It is a situation when the inventory comes to a constraint, either 0 or 1 at the last point.
Okay, I see. And the other question is that
That means that is when we enter the constraint.
oh, I understand. Okay.
Yeah. So
So the
that
other
one is I mean, it may not be. You have to construct the problem in a very way to be able to do that. You know what I mean? And I'm not doing it, but that's what happens. Yeah.
oh, I understand. Thank you.
Any other question? You know, the state constraint literature is very, very complicated. And there are still things going on in the literature. And my own view is that I think at some point, given the level of mathematics that's used for getting there, for us it is going further is actually is a point of diminishing return, so to speak, because the amount of work that you have to get there is so large It takes maybe 2-3 years of your time to figure out all that math, and the benefit is not that large. You see what I'm saying? If you do all of that 2-3 years, you might as well want to spend more time on stochastic problems, because deterministic problems are not that interesting to begin with anymore. Most of the time now, the stochastic is more important. So, oh, by the way, by that I mean that, did I mention that already or I didn't? Ben Susan has offered to teach a stochastic dynamic programming course. Usually Ben Susan goes to Hong Kong half a year, but his Hong Kong thing is going to be finished. And right now it is finished partly because of pandemic, I suppose. So he's going to teach a stochastic dynamic programming course. And there he is going to also do more on Brownian motions that we will not do much. We will only, my Brownian motion is all in appendix. We'll just, in chapter 12, 13, whatever, when you do stochastic control, we don't do the same rigor. And so I asked Ganesh to put Brownian motion in his course, but Ganesh said he doesn't have the time. And so now when Ben Susan decided that he's going to offer the course in stochastic dynamic programming, he will be able to do that. So I suggest everybody who takes my course, it's almost a prerequisite for that course. Although he would probably take students even without that, because he doesn't do as much maximum principle as he does dynamic programming. And you will see that at chapter 12, 13, we will also shift to dynamic programming. When it comes to stochastic problem, the maximum principle is a little less important than dynamic programming. By the way, there's a lot of maximum principle problems right now that are being published. We have just one paper that is going in Palm, which is major revision, under major revision. And the problem is pandemic problem. The pandemic problem, there is a model called SIR model. It's called SIR model. S means susceptible, I means infected, R means recovered. So from starting, when S and I become contact with each other, the infected will start giving suspicious, people who are susceptible become infected. That model is a standard model in pandemics going back many, many years. And you can now make it more sophisticated. So our model has uh, sophisticated in the sense that we have infected which are asymptotic, we have infected which are symptomatic, we have recovered that can infect, we have recovered that may not be able to infect. And so we have models, and then we have another model called patience. So we have a negative discount rate to model the impatience of the people who go into lockdown and social distancing. So we have a paper that is on pandemic that is under major revision in Palm, but the University of Washington model is a simulation model that actually gives you the prediction of all of that. It's also based on SIR model, but they cannot solve the problem using maximum principle. So but the model is still a set of differential equations. It's a dynamic model that goes from one point to another to see how the pandemic evolves. The space program is another one, which is clearly the stuff that got landed on Mars also had had a deterministic maximum principle kind of formulation there that they try to solve for those kind of problems. So there's a room for deterministic control problem. Right now it is. I can see many papers based on SIR. One is just published in the Journal of Political Economy, which is the top journal in economics. But anyway, in our field, you would be better. You would also be better off taking the next course that's built on this course from Ben Susan, and that's starting. I think it will start next semester. Okay, so what are we to do? I'm going to give you 2 problems from chapter 6 and 1 from 7, right? That has not been done yet, right? So I will do that because that's due 2 weeks from now. And the exam is next week. Exam is going to be coming from 1 to 5 chapter. I will wish you good luck in the exam. The questions are coming, as I mentioned to you, they are either in the book or similar to book. Sometimes a little bit of a change, but more or less all the methodology that we have developed will allow you to solve those problems. In that case, I think that's all I have to say. If there are more questions, you can ask me right now. Otherwise, I will talk to Kushali after this to make those changes that we just made. Okay? Thank you.